All right, good morning. Sorry, lots of things to set up, and I just don't have it down yet before 8 in the morning, but I hopefully will get there. So happy Thursday. This is actually a special day of the week for us because this is the last day of the week that we meet. So this is not Thursday for us. This is Chem Friday. Okay, mark that on your calendar. It's a special day, Chem Friday. So every Thursday for us, it's Chem Friday. All right, there is nothing on the screen. That's not good. I'm so observant. Let's see what we got going lights here. Oh my gosh. What the heck happened there? Oh, there we go. Bizarre. Was I just seeing that? Was that just me, or did you guys see what? Oh my gosh. Okay. Good start to the day. So as normal, please sign in for attendance. 7% of your grade, so thanks for being here. Don't forget about the homework assignments that are due Saturday. We'll take a look at those in just a second. That's your next thing that's due in this course. We are going to do a seating chart in here, and I'm guessing most of you have kind of figured out where you like to sit. And the reason we're going to do that is just, hopefully we don't have too many sick people this semester, but if you do get sick, then we kind of know where you were sitting. Maybe we can let people know that sit around us if you've been sick or not. So, but choose your own seat. Probably not Monday, just because it's a Monday. Maybe we'll do it on Tuesday. I'll just pass around a sheet. You'll write your name down. Okay, but choose where you want to be. Got to start class with some chemistry humor. What did the angry electron say when it was repelled? You guys got this one? If I can get it to scroll down. Oh, come on. Let me at him. That's pretty good. All right. Okay, let's quickly look at a couple of things. If things go well, the lecture yesterday did record, so that's a good thing. So if you happen to miss class because you're not feeling well or you oversleep or whatnot, at least you can go back and review the material. You might want to use this if there was something in class that you didn't catch very well, you might want to just go back after class, go back through it, and watch that recording. So folder at the bottom, I'll just dump the links to my YouTube channel in there, and then you can watch away, okay? So hopefully this will continue to work. I always don't quite trust it when I have two microphones and all sorts of things going at once, but we will see. All right, so this is what's due this Saturday. Orientation assignment, about half of you have done it already, so that's a good sign. Practice assignment, and then math review. Okay, so make sure you stay on top of those. Those are due essentially at midnight Saturday night, okay, 11:59 p.m. All right, any questions about the course, the structure, the assignments? Everybody's good? All right. All right, let's just get right back at it. So hang with me today. We're going to do a lot of math stuff, which I'd rather be doing chemistry stuff, but of course, in this course, in science in general and chemistry, we have to take measurements, we have to collect data, and we have to know how to express our numbers, we have to express our units, we have to know how many digits to carry in our calculations. And as we get to, at the end of the day, we have to know how to do conversions. And that's kind of going to be our main math calculation for the semester. Okay? So just to remind you where we left off with units. So I will say this again, I will probably say it multiple times throughout the semester. A number without a unit is meaningless. Okay? A number without a unit is meaningless. So always include units with your numbers. Clearly, units we're going to use, mass, we'll use gram, kilograms, milligrams, micrograms, nanograms. So we're going to get to the metric system in just a little bit. We will use length, meters, millimeters, micrometers, who knows, nanometers, obviously time, that's pretty obvious. Temperature, Kelvin is the SI unit of temperature. We will also use Celsius. We will briefly look at Fahrenheit, but we don't use Fahrenheit in chemistry. We just do not. Okay? We will not be using candelas and amps, but we will be using the mole amount of substance, so we'll come back to that. All right, so that's where we left off yesterday. Well, let me actually do this as a presentation. Might work better. Okay. Oh. All right. Oh, let me mention these on the right before I forget. Derived units. The cool thing about the metric system as opposed to the English system is that when we do cubic volume, okay, they're showing meters cubed here, but I'm actually going to jump to centimeters cubed. So if we take a cube that's 1 centimeter on an edge, okay, so try to picture, centimeters about the width of your pinky nail. So it's going to be a pretty small cube, but 1 centimeter on an edge. That cube will hold a volume of 1 milliliter. 1 cubic centimeter is 1 milliliter. Okay? And we're going to come back to that because we'll actually use that in this course. Let me get a pen here. Okay, let's see, color. Okay, so that's pretty cool. We don't have that equivalent in the English system. We can't say like 1 inch cubed is a cup, 8 ounces or whatever. It just doesn't work that way. Okay, so the metric system, not only does it make a lot more sense because it's all powers of 10, but then we have this relationship between cubic volume and fluid volume. We will use C velocity in this course, distance per time, and we'll typically see that when we start talking about light and the speed of light and things like that. Okay? And then density, of course, will be very important for us as well. So kilograms per meters cubed, mass per volume, that's what density is. We typically will use for density, just to write the unit down here, we'll typically use grams per centimeter cubed. Okay, again, mass per volume. And as you see at the top, cubic centimeter is a milliliter. So we can also write that as grams per milliliter. Okay, so that's the typical units of density that you will see. Okay, and just to let you know, you probably know this or may know this, density of water, obviously it does vary with, yes, you got it. It does vary with temperature, okay, because the volume will expand as we heat up that liquid, heat up the water. So as the volume changes, your density changes. But the density of water is about 1 gram per milliliter. About 1 gram per milliliter. Okay, that's always good to know. All right, we've already talked about the metric system a little bit. I expect you to know the common metric prefixes. Okay? I don't ask you to memorize too much stuff in this course, but you do need to memorize the common prefixes. So let me circle a couple of these, well, more than a couple. Let's start with kilo and then we'll go to milli, and then micro, nano, and pico. Those are the most important ones. Okay, how many is that? 5. That's not too bad. Does anybody see a pattern with those? Yes. What's that? I'm sorry? I still can't hear you. All ends in O. What? 0. Oh, yes. That's not what I was looking for, but that's okay. That's all right. No worries. Yes. They go by 3 powers of 10. Okay? Lost my train of thought. I'll get it back. So 3 powers of 10. So we don't need to, we could, I don't even know if they have prefixes in between these. Like we do have deci and centi and whatnot, but there's no reason to have prefixes in between. Every 3 powers of 10 is about all that we need. Okay? So these are easy to remember. If you go milli, and you probably know milli, 10 to the negative third, 0.001. Then micro, 10 to the negative 6, nano, 10 to the negative 9, pico, 10 to the negative 12, okay? We will use nano and pico because when we start getting down to atomic dimensions, we're gonna be using dimensions of picometers and nanometers. So think about that for a second. Picometer, a trillionth of a meter, okay? So if you ever get bored, I get bored all the time, and I do these little, just think about things. And so when I get really bored, I'll take a meter stick. So take about a yardstick. Meter stick is about 3 inches longer than a yard. Take that, and in your mind, try to divide that up into a trillion pieces. It'll take you a while, okay? But divide that up into a trillion pieces, and now you're starting to get down to the atomic dimension, okay? Down on the order of trillionths of a meter, okay? We will use kilo a lot, going the other direction. So kilo means 1,000. So in your mind, when we say kilo or use the letter K, think of that as a number. That's just shorthand for 1,000. Okay, it's just easier to write a K than to write numbers out. Same thing for milli. When we write M, that means a number 0.001, okay, or 10 to the negative third. And we can keep going down, okay? So we'll practice these as we go on, but please commit these to memory. Every once in a while, we will see mega, okay, 10 to the sixth, so larger than kilo. So we're multiplying that base unit by 10 to the sixth by a million, okay? So if we said a megameter, that's a million meters. All right, and the other one you will see, just because it's a common distance used, our common prefix for distance used is centi, okay? So you'll see centimeters quite a bit. And just to let you know, we'll talk about exact numbers in a little bit, but this is an exact definition that 1 inch, by definition, is exactly 2.54 centimeters. Okay, so look at your pinkies and go, okay, if I put 2.5 of those pinky nails together, does that get me to about 1 inch? Everybody's going like this. I don't know. But it gives you an idea about what distance a centimeter is. All right, so know the metric system. We will use, except for doing some conversions, and we will convert from inches to centimeters or, who knows, density in some weird English unit to metric system just for practice. But in science, we use the metric system. Okay? And we also use Kelvin and Celsius for temperature and not Fahrenheit. Okay, we kind of already went through these, and these slides kind of drive me nuts because I never know where I can write and where I can't. But if you look at that top number, okay, 6 zeros, so that's 10 to the 6th. So we could write that as 160 megabits. Okay, so there's one, and then we also have, and I kind of wrote over it, let me try to write this again. How many zeros we got? 1, 2, 3, 4, 5. So that, if you count over, you're going to get 10 to the negative 6th. Okay, so that's writing scientific notation, which we've already done, 3.2 times 10 to the negative 6th. And we can write that as, 3.2 micrograms. Okay, so again, if you don't see that letter as a number yet, you need to start seeing that letter as a number. When we write micro, and that's probably not a prefix you're that familiar with, micro means the number 10 to the negative 6th. So the number 3.2 times 10 to the negative 6th here, we just substitute that letter. And that's a Greek letter mu that's used for micro. All right, any questions so far? All right. All right, see if you can answer these 3 questions. Take a minute here. Either work alone or talk to somebody sitting next to you. How many meters are in a kilometer? How many amps are in a mega amp? And how many milligrams are in a gram? And they're really helping you out at the bottom, but just write those out real quick. If you have questions, let me know. All right, so how many meters are in a kilometer? 1,000. So kilo just means the number 10 to the 3rd, or we can write that as 1,000. We'll use scientific notation a lot, so we will write it as 10 to the 3rd quite often. Okay, so again, we are just saying, instead of writing the number 1,000, we are just writing the letter K, and that just represents the number 1,000. All right, how many amps in a mega amp? Yeah, 10 to the 6th or a million. Okay, so that capital letter M is just shorthand for the number 1 million, or 10 to the 6th. Okay, not that big a deal. Now, how many milligrams in a gram? Okay, 1,000. So you probably know that. Now, if you just look at the prefix itself, okay, so if we look at 1 milligram, milli means 1,000th, or 0.001, or 10 to the negative 3rd. Okay, but that wasn't the question. It didn't ask what 1 milligram was. It said how many milligrams are in a gram. okay? And it's 1,000. Now let's look at the math here, okay? Because we've said this is an equality, correct? We said what we have on the left side of this equal sign is equal to what we have on the right side, okay? So milli means what? 1/1000th, or 10 to the negative third, or 0.001, depending on how you want to write it, okay? So let's change that to the number that it represents. And I don't have a lot of room here. Let me come up here. So let's write this again. So 1,000, or if we want, let's write that at 10 to the third. Milli means 1/1000th, or in scientific notation, 10 to the negative third. So does 10 to the third times, oh, I'm sorry, I have to remember that this screen is shifted off just a little bit. Does 10 to the third times 10 to the negative third equal 1? Yes. Okay, when we multiply, we add exponents, add a +3 and a -3, and we end up with 10 to the 0, which is 1. Okay, so when you write these out, and we're going to practice when we get to unit conversions, make sure they're equal, because you're saying when you write these out that what's on the left is equal to what's on the right. And so just always double check that by just doing a quick little math calculation. All right, any questions? All right, we'll practice more of these. All right, I think about half of you maybe are in the lab part of this course or so some of you are not. But we do need to make measurements in the lab, and we need to know things about the quality of that measurement, okay? And by quality, we will define that in a number of ways. One way is to talk about accuracy and precision. Okay, how accurate is our measurement? How precise is our measurement? So which of these scales do you think is going to give us a more precise measure of mass? Yes, the first one, okay? So that's an analytical balance. We're not going to be able to weigh as much on that. We couldn't put that dog on that balance. Don't try that in the lab. Don't bring your dog in and try to weigh your dog on an analytical balance. That would be kind of fun, though. But the measurement we're going to get, well, I got ahead of myself. We'll get there. Let's do the definitions first. Accuracy is really how close are you to the true value? Okay, are you accurate? Is the number right? Okay. And precision is really how close multiple measurements are grouped to each other. Okay, so when we start talking about precision, we're going to use it in a couple of different ways. We'll talk about that its balance is more precise than the balance in the lower picture because of the number of digits we're going to get in our measurement. So that's one way that we use precision. But the other way is saying, well, we measured the mass 4 times. How closely did those measurements agree with one another? Okay, that's another way that we describe precision. Okay, so this analytical balance, okay, has a precision of 0.1, and I'm going to go to the metric system, milligrams. Okay, so 0.0001 grams, which is equivalent to 0.1 milligram. Okay, so we're pretty getting down there in terms of the precision of that measurement. Clearly, this balance is going, this scale is going to allow us to weigh out a larger mass, but we can only weigh within about 0.1 kilogram. Okay? Now, you might not have a picture of what a kilogram is. It's always good to know the conversion back. 1 kilogram is about 2.2 pounds. If you want to get some more significant digits on there, 2.205 pounds. Okay. So 0.1 kilogram would be about 0.2 pounds, a little over 0.2 pounds. All right, almost every chemistry textbook you look at has one of these in here. It's like a very common thing, but it is a good way to illustrate accuracy and precision. So we have a target here. And assuming we're supposed to hit the bullseye, what do you think about that data? Let's call it data, why not? Is it accurate? Yeah, I mean, we're trying to hit the middle of that target, pretty close. Is it precise? Yes, okay. So we would describe this as accurate and precise. Okay, close to the true value, and the grouping of those will make the analogy back to measurements. The grouping of those measurements are very close together. What about that one? Okay, yeah, we were trying to hit the center, so we didn't hit the center of the target, the bullseye. So we're not accurate, but we are precise. Okay, so our measurements all agree with one another. Now, this is the type of error you will see in the laboratory. Okay, you will see this type of error. This is called a systematic error. Okay, so we were just looking at balances. So in the laboratory, you may, before you weigh things out, you may need to calibrate that balance. So those analytical balances we'll have in the lab will have a little weight kit, okay, and it'll have weights that are like 1 gram, 5 grams, 10 grams, 20 grams inside there, and you can take one of those out, put it on the balance, and if you take the 10-gram weight out and put it on the balance and you don't read 10 grams, your balance is not calibrated properly, and you'll need to get your TA to come over and calibrate that balance, okay? So if your balance isn't calibrated, even if you measure everything correctly, you're gonna be off by, that whatever error that is, every single measurement, and that's called a systematic error, okay? So we will see that in the lab. So avoid those, and calibrating your balance is one of the things that you should do this semester, or at least just check that it is calibrated. All right, that's a mess. This is the kind of data you don't want, okay? Or we might also say this student was really lucky, because it's kind of hard to look at that, but if you average all of those together, they pretty much average to the center in this case. So this happens to turn out to be accurate, which seems kind of odd, because you would have to, in your mind, say, well, we're averaging our data, so you have to kind of make a leap here. If you took all those data points, you did those measurements in the lab, and you average those 6 data points together, you would get the right answer, okay? That's really lucky, and that's not the kind of data that you want, okay? Clearly, it's not precise. And then, what about this last example? Neither. That is, at least in this one, you got lucky in the lab. This one, you're going to be doing that experiment again, okay? So, not accurate or precise. All right, any questions on accuracy and precision? You've probably seen that before. But again, it's part of what we do. We need to take quality measurements. We need to be accurate. And you will find in the lab, you will do trials. Typically on an experiment, you'll do 3 trials. And they will need to agree with each other, or your TA will say, you need to do a 4th trial. Or you may need to do a 5th. Okay, because you have to have that precision piece as well. All right, another way that we represent the quality of our measurement, and you saw that with the balances, that analytical balance, 0.0001 after the decimal point, versus that larger balance that the dog was on, well, that's 0.1 kilograms. So that's, even the other way. So we will talk about how many digits that we express in our answer. So take a look at these. Here's 40, 60, so that would be 50. So what do you think the volume is in that beaker? Yes. 40, I hear 44, I heard 49, I hear 40, 49, I heard something else over here. 48. Any other estimates? I didn't hear you. Okay, so we got 48 and 49, okay? So what we consider our last significant digit, and when we express a number, that we're saying there's uncertainty in that last digit, as we saw in just the answers we got. We got 48 and 49, okay? So I think the book says it's 48, but again, let's see. Okay, so they say 48, all right? So 48 or 49, but typically, so that last digit, this one here, okay, so that 8, we're typically saying there's an uncertainty of plus or minus 1 in that last digit. Okay, so 48 plus or minus 1, and let's not forget our units, milliliters. Okay, so that means that volume probably between 47 and 49. Okay, certainly not 50. We know it's not 50, so 47 to 49 seems about right. Okay, so that's the beaker. Let's go to the graduated cylinder. And that might not be easy to see here, but let's throw out some numbers on the graduated cylinder. Yes. No, we'll do this. So like if you use an analytical balance, we would still say in that last number that you read, there's going to be an uncertainty of 1 in that last digit, unless you specify otherwise. Okay, so sometimes in scientific papers you'll read the uncertainty might be larger than 1 in the last digit, and that's just based on, maybe they did some statistical analysis or something where they determined the uncertainty to be larger. Okay, but just in a straight up measurement, generally plus or minus 1 in the last digit that we report. All right, what do you think about the graduated cylinder? Okay, 47, any estimates past 47? Is it 47.0? Okay. Any other? We got 47.0 and 47.5. Anybody else? An uncertainty of 1, okay. All right, so let's start with this. So 47.0, then we would be saying plus or minus 0.1 because it's the digit after the decimal point. So maybe we're saying it's between 46.9 and 47.1. I don't know, okay. So in your textbook, you'll see that they're reading that again. You do your last digit, you're estimating. Okay, now reading this on the screen, if you were in the lab, it might be a little easier to see. The conclusion there is that the meniscus is slightly above the 47 line. Okay, but if you recorded that as 47.0, that's fine. There's uncertainty in that last digit. And you would be within what the expected uncertainty in that reading of that measurement would be. Okay, so graduated cylinder, it's more precise. It's a better way to do volume. You really don't want to use a beaker to measure out volume in the lab because you just don't have the precision that you have with the graduated cylinder. And there are more precise glassware that you'll use. You'll use pipettes in the lab that are going to be more precise than that. Okay. So again, significant digits indicate how precisely we know a measurement. Okay. More digits in the reading from the graduated cylinder. 3 significant digits. We're going to do digits right now. Any non-zero digit is significant. So 47.1 has 3 significant digits. 48 just has 2. Okay, so more digits, more precise in this case. All right, so we already did that. Let's go. All right. I wanted to get to unit conversions today, and I am going slower than I thought I was going to go, which is pretty typical, but we'll see where we get. All right, so let's do significant digits. It's again, quality of our measurement, accuracy, precision, but then the more digits that we have, whether it's mass or volume, would tell us the precision of our measurement. Non-zero digits are easy. They're always significant. All right. The digits that you have to be careful with are the non-zero ones, because there's really 3 different types of zeros. There are 3 different types of zeros. There are what I like to call captive zeros, okay? And that's what you see there. That 0 in the middle is held captive by those non-zero digits. Okay. And those types of zeros are always significant. And that says that in the text. Okay, so non-zero digits just count 1, 2, 3, 4, 5. What about the second number? That's also 5. All right, other type of zero. So captive zeros, always significant. Trailing zeros, okay, so those after a non-zero digit, they're significant if there's a decimal point. Everybody hear that? So if there's a decimal point there, those trailing zeros are significant. Okay, so how many digits in this number 5.00? 3. Okay, and they're trying to show you we're saying by expressing it to 5.00, we have uncertainty in that last digit, so we're saying that measurement is somewhere between 4.99 and 5.01, and so we have 3 significant digits. Okay, but trailing zeros are significant if there's a decimal point. All right, any questions so far before we move on? Okay, non-zero always significant, captive zero is always significant, trailing zero is significant if there's a decimal point. One more type of zero is leading zeros. And they're missing a decimal point here. It should be right there. Okay. Leading zeros are just placeholders. It's just showing you where that decimal point is. Okay. So leading zeros are not significant. So 0.000012. Yes. So, well, captive zeros are zeros, but they are significant digits. So if you're counting how many digits do you have in that number, they count as a digit. These zeros do not. Leading zeros do not count. So both of those numbers have how many significant digits? Just 2. okay? And they're doing a comparison. So that number, 0.0045, we could write that as 4.5 millimeters. And just to make sure we see that. So this number, 123, so we could write this as 4.5 times 10 to the negative third meters. Everybody agree with that scientific notation? Move the decimal point 3 places, 4.5 times 10 to the negative third. What prefix means 10 to the negative third? Milli. Okay, so 4.5 times 10 to the negative third meters can also be written as 4.5 millimeters, because milli just means 10 to the negative third. So how many digits in 4.5? Just 2. So they're just trying to show you there that those zeros are really just placeholders, that they're actually not significant. So leading zeros are not significant. All right, so we just went through this. All right. All right, last thing to consider in terms of significant digits. What if we have trailing zeros and there is no decimal point? Okay, and the answer is we really don't know. Okay, it's really not a very good way to write a number, particularly if you're recording a number as a measurement. Okay, so never in the lab report a number with, we wouldn't measure $10 million in the lab. That would be kind of nice. Man, we got lots of money here at NAU, right? Well, everybody gets $10 million when they go in the lab. But don't report numbers like that, okay? And we will typically use scientific notation to avoid the situation where we have all these zeros and we don't know if they're significant or not by how that number is written. You know, so if those zeros are not significant and it's just the 1, you know, that means we have somewhere between $9 and $11 million because the uncertainty is in that first digit. Okay, I'd be okay with that. I'd take between 9 and 11 million. I'd be all right. But you know, do we know this measurement or this number more precisely than that? Here's an example where they're saying, well, we actually know it out to here. So how would we express that number? Oh, I don't like sometimes what they do with this book, so let's go back. Let me just show you how I would write this number. So say that we actually did know that these zeros, 1, 2, 3, 4, were significant. Okay, so let's say these 4 are significant, but these 3 are not. So how should we write that number? Okay, so you could write it as plus or minus 1,000. Okay, that would be one way. So you're now saying, so that since this is, 1, this is in the thousandths place, we could say plus or minus 1,000 here. But probably a better way, if we write this as in scientific notation, 1, 2, 3, 4, 5, 6, 7, 1.0000, because I'm saying those 4 zeros are significant. Okay, so that's what we're going to do. We're going to write it in scientific notation. If I write in scientific notation, you will note there is now a decimal point here. So when there's a decimal point, those trailing zeros are significant. So when we write it in scientific notation, I'm saying those 4 zeros are significant. And that's crystal clear. There's no ambiguity in that number. So then we look at this, 1, 2, 3, 4, 5. Okay. we have 5 significant digits, or if we want to shorthand that, we'll just say we have 5 sig figs. Okay? All right, so we'll practice more of this as we go on and write out numbers, but if there's any uncertainty with trailing zeros, in this course, write it in scientific notation. And I think this next one they get at the writing the plus or minus. Never mind, we'll skip that. All right, just to sum up here, and we might not get to unit conversions, darn. I actually really like unit conversions, so I hope you do too. Non-zero is always significant. Captive zeros, however you want to stay, they just say zeros between non-zeros. I call those captive zeros. Trailing zeros are significant if there's a decimal point. Keep that in mind. Leading zeros, not significant. And don't write numbers like the bottom number. Write that in scientific notation to avoid any ambiguity there. All right. Let's skip exact numbers for now, just because in the last 2 minutes that I have, I just want to, never mind. So what I'll do, I sometimes have don't back up yet. Give me 1 more minute. Sometimes I have grand visions of where I'm going to be in class, and I really had this grand vision that we would be doing unit conversions today. So I apologize to all of you for doing a pre-lecture on unit conversions, and we didn't even get there, okay? If you did not get that pre-lecture done, since I didn't get there, most of you did. It was like 67 out of 70-ish people in the class. I will reopen that for Monday, because we're going to do unit conversions on Monday. But to wrap up today, let's kind of wrap up numbers. We've done precision and accuracy. We've done significant figures. Let's wrap up with exact numbers, okay? And earlier today, I did say 1 inch by definition is exactly 2.54 centimeters. That's to make a connection between US system of distance and the metric system of distance. But anytime we count something, that would be an exact number. In this case, we have exactly 7 pennies. Any of the metric conversions are exact. Okay, they're all powers of 10, right? So when we say there's 1,000 milligrams in a gram, that's exact. You have as many significant figures as you need. Okay, don't look at that and say, oh, well, it's 1 gram, so there's only 1 sig fig. No, that's a metric conversion, infinite number of sig figs. Same thing even if we're using our US system definitions. By definition, there's exactly 3 feet in a yard. We won't use that very much in this course, but so that what we'll start with next time, just to just give you a little preview of next class. Before we get to unit conversions on Monday, we will do a few calculations with sig figs. What happens when we multiply them together or we divide numbers? What if we add or subtract? How do we carry sig figs in our calculation? Okay, so I apologize. I didn't quite get to where I wanted to be today, but we're fine. We will finish up chapter 2 early next week, and we will start chapter 3. Okay, I hope tomorrow to have your homework and quiz for next weekend posted if people want to work ahead. You don't have to work ahead, but some people like to get ahead. So I will tomorrow get up next weekend's homework and quiz. Have a wonderful weekend. It's not the weekend yet, but I will not see you till Monday most likely. I do have an office hour right now after class, so you can come see me, or you can come down right now and we can handle a few questions while we're here.